So welcome to this second run-up at, yeah, thanks, okay, to the Nobel Prizes. So last week was on quantum physics, this is on quantum physics. They overlap a lot, last week's and this week's. They do. So all that stuff that you fully understood last week is applicable partly to this week. You get credit for that. And but it really started last year with the the prize in physics, quantum. It'll cost you for that chair. Yeah. And so, but remember that one about Einstein, the last challenge to quantum physics, and Einstein's challenge to quantum physics. I really enjoyed that one last year. That's when I really started to get interested in quantum physics. Oh, more chairs.
Hang on,
Oh, here's the chair.
Excuse me.
Oh, you all right? Okay, so anyway, so this is the third in quantum mechanics. Next week, it's more prosaic. We're talking about the COVID vaccine, mRNA vaccine. But very interesting from the personal aspect of the two principal scientists in that study. Very, very interesting. So that in itself is worthwhile coming out for. Now this one is about, well, I entitled it Chemistry Squeezing Electrons of Light. Well, that's kind of what it's all about. Distorting or compressing atoms together, and that forces electrons to take different paths and behave differently, and therefore emit a different light when they're smaller. The crystal is a lot smaller, so that's what it's really all about. But you know, going through these Nobel Prizes, this is now the 7th year for me. It isn't just about this prize, because there's a broader, you may not have much sense for this, but I have a growing sense of it. There's a broader revolution taking place in the basic sciences, and a coming together of quantum mechanics, chemistry, biochemistry, genetics, evolution, natural and unnatural, and diseases. And where is that little thing? I mean, I pick up, what was it, from Nature. The first paper I've ever seen where they tied the quantum mechanics to evolution. Now, of course, they're linked. You know that, because everything's ultimately made of quantum particles and sources of energy and that kind. You know that, but really? And it's a very, very interesting study. So I thought, okay, that's where we're going. And the other thing, too, we don't think of this. We think of quantum mechanics as all subatomic. It isn't, really. The shape of the earliest universe, or the earliest time in the universe, was shaped by quantum mechanics and Heisenberg's uncertainty principle. That's why when you look at the cosmic background radiation, let out 380,000 years after the Big Bang, you see this clumpiness. And the radio wave background, but also the temperature of the universe. It's that clumpiness that allowed stars and galaxies to form. Without that clumpiness, no stars, no galaxies. That's a quantum, that's a result of quantum effects spread out over a gazillion miles. So it's all of this stuff is coming together. So one thing I did want to do, I wrote an article, Nanoparticles of Light, the Nobel Prize in Chemistry, this year. And it was really written to my father. So I'll read the first paragraph, I'll read the last paragraph at the end of it. But there was a professor, by the way, in my second year undergraduate stuff at Western, who was a very lovely man. He knew my father well, which I didn't know. And he taught me organic chemistry. So here it goes. Your father would expect better, and so do I, was what my organic chemistry professor told me in my second pre-medicine year at the University of Western Ontario. My father was a chemical engineer and good friend of Professor Baldwin, I didn't know it then, who was a soft-spoken, kind man but had little patience for those who were lackadaisical, me. One of several cautionary words he applied to me that day. So that is the start. And frankly, I didn't pay any attention to chemistry for the next 30, 40 years until the genetics revolution came along. But the Nobel series has really grabbed me. Now I get it. And I get why it's exciting. And it's almost an exponential increase in interest right now for almost anyone who knows anything about it. So we'll maybe catch that as we move along. So here we are, squeezing dots, electrons, and light. That's my made-up theme there. So I want to say something about winning a Nobel Prize because you know, it's not just about this specific award, it's all of them. Many win Nobels later in life, you know that. It's almost a survival award. You know that John Goodenough got it at 97, Roger Penrose at 87, and John Goodenough was good enough, more than good enough, but it was for work he did at Oxford in the 1980s on the lithium-ion battery. Just a remarkable guy. I mean, this guy was dyslexic and a very bright guy, and he decided to fix that by teaching himself Greek and Latin. He got the top marks at Groton College. Then he went on to Princeton, got the best marks there. Then he went on to Chicago with a particle accelerator lab, Fermi lab, did very, very well there. Then MIT, it's like a list of great places. And that's a lesson for people, young people. If they have ambitions, go to good places that can foster you. And then because the funding was cut off or some stuff that he was involved in, moved on to Oxford, and that's where he did his stuff. Anyway, some people have said that Nobel Prizes, given the age of some of them, it's a lifetime achievement award, and it is that, I think, for some. Peebles is one. He just did a lot of really good stuff, and if you put it together, you realize that this guy was worth a lot. And he did a lot of work on the evolution of the early universe, the Standard Model, by the way, which needs a lot of revision these days. Winning a Nobel Prize is a life-changing thing for most laureates who aren't at all used to all the attention they get from the press. Now, this is a flickering light that flickers brightly for a few weeks and months and doesn't go on. But still, they get a lot of speaking engagements, book deals. One person was interested in this, David Schultz up here. Okay, what happens to Nobel laureates? Do they continue on to do great stuff? Turns out they don't. They kind of, some of them kind of peter out. No surprise if you're distracted by a lot of talks, if you're running a big lab, and you're just not around to do this stuff. And it's not that they're lazy or anything like that. Some of them become public intellectuals. I mean, people go to them as if they know everything about everything and ask all kinds of arcane questions that they have no skills of talking about, but are fond of some of them talking about. Now, there are exceptions. This guy, Arden Pataputian, amazing guy. He did the really great stuff, what is it, 2 years ago, by identifying the genetics and the structure and the function of specific sensory receptors, especially temperature and touch pressure. It was very elegant. And this very sharpless, we'll be talking about today, this is his second Nobel Prize this year. And he deserves both of them, for sure. And we'll talk about why. He's one of these older ones who continues to be very active and sets the pace. Lessons learned from Nobel Prizes? Well, I've said this before, the Nobel committees in the sciences are very conservative. They want evidence. They're not going to give any award for, I mentioned last week, for black holes unless somebody's seen a black hole, actually. And then the award came immediately the next year. But of course it invalidated Stephen Hawking, who was dead by that time. So for large projects, the awards usually illustrate the importance of collaboration. This brings up an issue with Nobel Prizes. How do you identify 1, 2, or 3 people when you know it's a large lab and there are a lot of undergrads, postgrads, postdocs, visiting profs in the lab, all making significant contributions? So where's the authorship? This is certainly true with Niels Bohr. He was a very social person. I mean, he worked stuff out by kind of discussing it with groups of people. It's hard to know the authorship in Niels Bohr stuff, but how much was him? How much was anyone else? And it really doesn't matter. What matters is the product at the end. Sometimes they make mistakes, but for the most part, they actually do a very good job. It would be wrong to think that the Nobel Prizes represent everything that's great in science. They do not. There's a lot of really good stuff that's left out. And after all, these are human decisions. Now, and there was an article that put me off a little bit in Nature. This Neil Savage, meet the unsung scientists behind the quantum dot model, which we're talking about today. Well, actually, if you read the article, they talk to the various several graduate students and postdocs that work with the Nobel laureates of today, and glowing comments about them. They love working for them and with them. So unsung they may be, meaning not included in the Nobel list, but certainly not what they felt. They felt privileged. They had a wonderful time with these people. A lot of Nobel Prize winners are very collaborative, and they look after their own. That's why the labs are so productive. So on we go. And then, well, this is the one that keeps coming up, this unfairness thing. And one of the examples is Rosalind Franklin. You may have heard this woman who did X-ray crystallography in the 1950s and made a very significant observation about the structure of DNA, at least seen using X-ray crystallography. How come she didn't share the Nobel Prize? Actually, it's her boss that shouldn't have shared the Nobel Prize. But you know, that's a European model in those days. Give credit to whoever runs the lab. And in those days, all men. Not so these days. And so, anyway, that's a good thing. Well, you've this is the second or third time I've showed you this. The Nobel committees in sciences pay a lot of attention to this approach. So this is the American, and who laid down the rules for science this way. I'm repeating it myself. But in general, we look for a new law by the following process. First, we guess it. We imagine it, would be another word here. Then we compute the consequence. If that's what we thought, if this is the idea, then what would be the consequence? If this actually played out, what would the implications be? That makes sense. And then you look for the evidence. And if the evidence doesn't support it, it's wrong, period. And as he points out, if it disagrees with the experiment, it is wrong. Very emphatic. In that simple statement is the key to science. This is his comment. It does not make any difference how beautiful your guess is. It does not make any difference how smart you are, who made the guess, or what his or her name is. If it disagrees with the experiment, it is wrong. That's all there is to it. That is at the foundation. That was behind the black hole thing. That was behind Einstein not getting a prize for general relativity, which he should have, except they awarded it to him the back way in 2020 by giving it to Roger Penrose. So that's a big thing for them. Well, there's the ceremony. You probably saw this kind of stuff on TV. This is this year's Troika, and here's the thing. Here, they're different particles, the same particles, exactly the same crystals in every single flask here, except that the crystals are larger here than they are in the blue at the end, illuminated by light. So with the large crystals in this one, it's the longer wavelengths, hence red. And then intermediate lengths in between, and the shortest wavelengths on the right side. That's the foundation of today. Remember, it was something I pointed out last week. Okay, so we'll get into this. But one of the things, this voyage here had a few jogs on the way to get to this year. Remember, this nomination process goes over several years. There are several things that are on the go. They try to fit them in almost a temporal order, year by year. So it's good to know what went on before. And this is one of this is the nature of molecules. The chemistry of stars, you may not realize this, including fusion and the making of the elements, is far simpler than any biological system. We are far more complex than the stars. Far more complex, chemically speaking. Nature, by that I mean the laws that govern quantum mechanics, chemistry, biochemistry, chance, and evolution by natural selection. By nature. Nature creates the most complex molecules of the universe. And they do it, and it does it with efficiency and ease. Does it easily. Before the advent of directed evolution, which I'm going to talk about in just a second, click chemistry last year, and AI big time. In the last 2 decades, creating complex molecules was very challenging. It was almost an art, an artisan's activity. Well, along came Frances Arnold, and she's one of my heroes because she wasn't one on everyone's radar scope, and she surprised people. And she was doing some work trying to develop better enzymes. Enzymes are proteins, the kind that speed up reactions, facilitate reactions. And it was extraordinarily difficult for her. I mean, proteins they're made out of 20 amino acids in varying order. And, but the molecule itself might be hundreds, even thousands of amino acids in size. So you can imagine these are really complex. And the order dictates the shape dictates the function. So form follows the order, and the function follows the shape. Why? Because it exposes certain groupings that are active or inactive, whatever it is, and it changes the chemistry, how these proteins work. There's been a huge revolution in that just in the last year. An Lasker Prize, which is the American Nobel Prize, and often a prelude to a Nobel Prize, this year Lasker Prize was given to AI-directed deciphering of the shape and therefore function of proteins. It's a huge change. So, so what did Frances do in this? Well, she was very frustrated going about it in a rational, orderly fashion, the way a chemist would do it. And, to leap to this, that's one of those great ideational, it's one of the things that the Nobel committees love, something that's really innovative, groundbreaking, that no one else thought of. And she said, okay, nature does a really good job. Why don't I turn nature on this thing? Why don't I let evolution create a better protein, a better enzyme in this case? That's exactly what she did. And she was working on a particular enzyme, I can't remember what that enzyme does, but anyway, created random mutations in the enzyme's genetic code, introduced those mutated genes into bacteria, which then created variants of the same enzyme, and then she had them compete against one another and chose the winner, and then went through several cycles. And if she went through enough cycles, 200 times, in this case, the enzyme was a lot more effective. It was just a really clever idea that no one had thought of. And she had hundreds of other people in the field competing against her. And she wasn't a known entity at that time, so she did a great job. Well, then, here's the Nobel Prize for the lithium-ion battery. I must say, I'm a big favorite of John Goodenough. I love his name. He's one of these interesting people. I've been very interested. Are people productive in later life? Well, there are outriders. John Goodenough's one of them. And so is Roger Penrose, doing really good stuff late in life. He was working in a lab a few months before he died at 100. And so was he good enough? Yes, he was good enough, biologically and as a scientist. And a very good collaborator. By the way, he's also an Episcopalian, a very active Episcopalian. So if you're worried about religion and science, here's one of the examples. A very fine fellow. I won't say anything more about that, but listen, here are the stars. We're not looking at old people now. We're talking about gene editing, 2 women. That's a big deal. They beat out the male group at Harvard. Gene editing was, this is a very new field, it's less than 10 years old. Everyone recognizes this as a big deal, a transformative one, and they chose, actually it was Carpentier here, recognized or was told or learned about how bacteria kind of recognize viral invaders and kind of store the information away in their little memory bank so that they can recognize it when it comes in again and kill it. And how did they kill it? By creating a guide to it with an enzyme attached to it, which destroyed it. And then she and Jennifer thought, oh, well, isn't that interesting? Nature's already solved this problem for it. It's already edited genes, and it's doing a really good job of it. Why not do the same thing? We'll create a guide molecule to find the place on the gene that we want to modify. In other words, I'm 180 Gage Street. It has an address. That guide will take the guide to 180 Gage Street, and then it has an attached enzyme that when it gets to 180 Gage Street, it cuts my hedge, or it cuts both strands of DNA, right? Very clever, really clever. And my favorite picture, which I could not find on the internet, and I couldn't find it in my stuff, somewhere it's there, is the 2 women walking up to the podium to receive their prize arm in arm. They're good friends. They were good friends. Not all the time, but good friends. And certainly very good colleagues. And there they are, not a great picture, but there's Jennifer and her French colleague, who, by the way, is now the head for Department of the Max Planck. So that's a premier place in Germany, as good as any American place. And so there they are, the 2 of them. Well, I've already described what happened, so I don't have to do it for you now. But, fields don't, gene editing as they imagined it, and for which they won the prize, isn't perfect. It's pretty close to perfect, but it's like going back to the 180 Gage Street analogy. Well, it could be on either side of, Gage has 2 sides split by 55, and it could be either side. Both homes, as it turns out, are white frame homes, that kind of thing, so you could make a mistake. So the guide is a sequence of bases. And if there's another place in the DNA where that pattern is almost exactly the same. It looks like wedding gauge street, but it isn't. Then the guide may attach to that and slip in. So unintended consequences of gene editing. Well, it's gone along, so here we are, advances in gene editing. The other thing with the original method was that they kind of left nature to fix the cut, the Band-Aid here. Well, not so these days. They don't take any chances. They have specific bases that they want to insert in that place, so they may cut out a piece, but they put in precisely the right patch. So that makes a lot of sense, gets around some of the errors. So here we are, the super precise CRISPR tool has its first trial, Nature. So this tells you it took 2 or 3 years to kind of get there. Here's one, we're talking about the flu, or talking about flu, and changing the flu vaccine. That's going to happen big time the next year or two, instead of this mess that we have every year. Perhaps because of gene editing. Well, here is, this is a favorite year for mine. This is last year. And this is all about making proteins. Again, on that same, there's Barry Sharpless at the end, who won the Nobel Prize back in 2001, and another one last year. She is impressive. It's Carolyn Bertozzi. We'll talk about her a little bit later, but she's very impressive. Stanford University, Scripps Research Institute of the USA, I think of as a long-term home for long-term care for Nobel Prize winners. That after they've kind of reached a certain age and level of productivity, like Crick ended up out there and spent his time in the library. So a nice place for graduate students, a place to meet famous people, and I'm sure a nice accommodation lab and all that kind of thing. But Sharpless remained sharp. Right, so there they are. I like this little cartoon, and it was all about Lego, clipping pieces together. And Sharpless's really great idea here. Look, it's really difficult constructing proteins, complex ones with many amino acids in them. And it's kind of an art form. And Sharpless said, look, we've got to bring some order to all of this. So his bright idea was, well, let's break it up. Let's put together smaller pieces, some of them off the shelf, that we can literally chemically click together. And that's what he did, so-called click chemistry, by attaching 2 groups, one to one, to the patch, and one to the other, or at least at both ends, the 2 pieces that you want to join, and those molecules kind of click together and form a very strong bond, and then go on and add the next segment. So I put in the ages up here. There's Caroline Bertuzzi, 56. Now that's when she got the Nobel Prize last year, so 57 now. Her creative work would have been in the 15 years before that, right up to that time. She runs a very active lab still now. I don't know why they gave it to Morton Meldell. He essentially came, well, I won't say anything more, but anyway, I don't know why they included him. Sharpless for sure. He's the father of chemistry these days, the honored person. But she is incredible. So we'll go back or forward. Now, just a little bit about this. There's a bit of the arcane language of the Nobel Committee when they award stuff. It isn't quite how we would put it, maybe. And so the Royal Swedish Academy, now this is in English. By the way, I found out that Sweden, or Swedish language, is about 20% shorter than English. And English is shorter than French. Yeah, so the Swedes are saving on letters, right, and words. Anyway, the Royal Swedish Academy has decided to award for click chemistry. their work, I think, this is me here, their work was beautiful, elegant, especially Bertuzzi. Elegant and a compelling story of how the best scientists work by defining the challenge and figuring out how to solve it and working collegially toward the answer. Her lab personifies that. Everyone in that lab is very loyal to her, and she is loyal to them. They work well together, and they've been very, very productive. If you're interested, she's gay. Doesn't make a whit of difference. So here's the story before 2000. So this is the big change, the beginning of the big change in making proteins. Before 2000, making these complex molecules was very challenging. It was almost like artisans working, meaning they could make one molecule at a time, one protein at a time, but it wouldn't, there was no payoff in creating the next protein. You know, you had to do it a whole other business with that. And it consumed a lot of time, and it was very costly. In a word, frustrating. And so here's sharpness. So Nobel Prize 2001. And he realized that the efficient manufacture of complex molecules would strongly benefit from streamlining. Well, I've already described that process just a few minutes ago. So rather than relying on the old artisan approach, he came up with this click chemistry. The click chemistry, that phrase, is big in the science community. Everyone recognizes what click chemistry is. Well, it's right in the first article. Click chemistry, the first word. And diverse chemical functions from a few good reactions. It was beautifully, you know, it takes cleverness to, more than cleverness, imagination and creativity to come up with ideas like this. It really does. And that's what the Nobel committees I mentioned earlier, that's what they look for. That plus evidence. Well, this is a little cartoon picture of there are two groups, azide and alkyne right here. There's alkyne and azide. They're both sides of the click, the two Lego pieces that come together. Attach an azide group to this molecule, attach the alkyne to the other one, like a belt or that kind of thing, snap them together in the presence of copper. And it's a very stable bond. The problem for Bertuzzi, who worked in biology, you can't use copper as a catalyst. Copper is toxic. So she had to find another way around this. And she came up with two really good ideas. And so, as I said, Bertuzzi had another bright idea. So it tells us something of her character in this. I mean, she's clearly frustrated. Her group spent 4 years trying to solve this thing, and were really frustrated. And then, during a seminar, she listened to a German scientist to explain how he had succeeded in getting cells to produce a variant of sialic acid. That's a sugar-like compound. One of the sugars that makes up the group of sugars, glycans. The thing that struck me when I read this, I've been to a lot of international science meetings. They're PowerPoint presentations. They're boring as hell, most of them. They're certainly not presented in any way that would keep you awake. And but Bertuzzi's one of those people, and there are maybe 10% people are like this. They're kind of genuinely interested. And they go to this stuff, well, how else are you going to learn about it? And so she showed up and got the idea from listening to that scientist explain how he could get cells to produce a sugar molecule. And then she thought, okay, she's going to use a similar method to get cells to produce that sugar, but with a difference, with an attached chemical handle. And that chemical handle could be a fluorescent molecule. So if you had, this is like a tracer, isn't it? You're attaching a tracer, a fluorescent molecule, to the molecule that you really want to study. So you need something to light it up. Well, that's what she's done. That's exactly what she's done. And never mind the chemistry over here, very, very successful, because here's the nucleus of, these are all cells here, and that fluorescing around the rim, or just under the cell membrane, that's all one specific sugar. And the cell, so you can actually see it in action. It was a beautiful, beautiful technique, and she developed it. That's why she got the Nobel Prize. And then this may be even more arcane, but pay attention. This is the committee. Role of ideation and conceptualization, not two words I would use, but modern chemistry is driven not only by important discoveries and improvements, but by the formulation of concepts that catalyze and accelerate a new. So they're looking for something that will grow a field, something to spark a change, a revolution in a field. That's what they're looking for, plus the evidence. And I think that this is absolutely right. As humans, we all need occasional, sometimes surprising eye-openers to stimulate our minds and concepts to energize and expand our comprehension. I don't think there's enough people in our age group that do that, or even for that matter, in the Middle Ages. So that's really good advice. Whether you're painting something or writing something or working in your garden or whatever it is, good stuff to do. Well, here they are. Nobel Prize in Chemistry 23. So Alexei Akhmov from the Soviet Union, the former Soviet Union. A well-recognized scientist there, quality person. Louis Brou for those two together, for the discovery and making of quantum dots, and Randy Wandy, who revolutionized their manufacture. I mean, there's no good having these dots if you can't create a lot of them reproducibly and precisely. And some of the applications, quantum dots now illuminate most TV screens, computer screens. I thought of that when I had my Apple computer out today. And there are lots of other applications, including for surgery. Because if you shine a light on the surface of the brain, for example, neurosurgeons are using this now, you can actually identify malignant tissue or relatively ischemic tissue just from the light that you shine on, not so much that, but the light that's reflected back from it. And boy, that's a gift, because you sure can't do it by hand or just visually do that. So that's a big plus. And here they are, looking very happy. You can tell first generation. So here's the first generation. These are the older ones. The guy from Russia and now in the United States, now retired, incidentally. Louis Brou, he's one of his doctoral students, David and Valmai. So he knew all about this stuff because he was working in this lab 15 or 20 years before. So it pays, as I said earlier, to be in a productive lab. And where did they come from? Well, there's Akhmov, so there's no Y on here. 78. This is a very interesting history, because this was, in those days, people in the West hardly knew what was going on in Russia, what was being published. Well, number one, they couldn't read Russian. Number two, some of the stuff they didn't have access to. The CIA actually paid people to translate Russian documents. And I'll say a little bit more about that later, because that's what led to stealth technology. That technology came from Russia. It was in a Russian obtuse paper, picked up, translated by the CIA, Lockheed Martin, the Skunk Works, recognized what those equations actually meant, and acted on it. So their first, 117A, the first stealth, the first one in the Iraq War,
Okay, so you remember that. Louis Brute, so born in Cleveland, again, Columbia University. And he was in New York and worked for a time at its nanocrystal technology company, but now retired. Bawandi, there's MIT, one of the 2 or 3 best engineering schools in the world, I think.
So background does make a difference. And the other thing that that happens with big places, I mean, I remember that in the times I've been in Oxford, kind of important people come through those places. So your chances of encountering them are a lot higher than if you're some peripheral institution, because they don't go through your place. And so that enriches the environment. So anyway, quantum effects, here it is simplified. Here's an electron in a, say, a particle or inside an atom, but there would be a bunch of these in a crystal, but just isolating one. You know that electrons from last week can have wave-like properties as well as particle properties. And what happens is if you make the crystals smaller and smaller and smaller, it compresses the atoms, and it forces the electrons to take different paths around the atom. That's why they change their properties. That's why they change their behavior. That's why they emit different light at different wavelengths. And so this is the Nobel Committee. By the way, this is a figure from the Nobel Committee's kind of paper on this stuff. I kind of like to borrow their stuff as you're looking at the original material. The size, this is an astounding one. A quantum dot is to a soccer ball as a soccer ball is to the Earth in size. I mean, can you get your head around that? I can. We're talking about 1/10,000th of a single human hair. I was looking at one of my hairs today and I thought, 1/10,000? Really? And of course that's not the atom, that's a bunch of atoms forming a crystal. So it's already kind of very, very tiny. And the history of quantum dots, well, it has an interesting history which we're not going to go through right here because it's picked up later. I like this because glass has been a fixture in medieval cathedrals and magnificent colors, and there were artisans that understood this, and they knew how to mix the stuff, to mix silver, gold, or cadmium, or other elements with glass. But don't you love the expression of, that's why I made this move, tested their way to an understanding of how glass could be produced. That is a very important sentence or phrase. Isn't that how chefs work sometimes? Is that how artists work sometimes? We try stuff, and if it doesn't work, we try again. It's probably how they worked in Paleolithic times, on the hunt or whatever they were doing. Trial by experiment. It's a wonderful phrase to cover this. So in the 19th and 20th century, now recognize that quantum physics did not exist until 1905, 05, when Einstein produced that paper on the quantum nature of light. It absolutely exploded from 0, it's like inflation in the universe, to 30 or 40 years later. Absolutely exploded. And so when we talk about people in the 20th century beginning to produce glass, figuring stuff out in here, they already understood theoretically the implications of quantum theory for this bizarre thing that the smaller the particle, it mandated different light. They understood that. It's an outcome of theory. Here's the important thing here. Confined to a tiny space, compresses the wave-like properties of electrons such that if stimulated by an external light, for example, the electrons of smaller quantum dots emit blue, shorter wavelength light, and larger ones, longer wavelengths. That's the key.
remember nothing else from today, that would be it, a good one to remember. This guy's interesting. He produced glass tinted with copper chloride. I mean, it looks like a chef doing stuff, right? Between 500 and 700 degrees centigrade varied the time from an hour to 96 hours. So what did he find? Once the glass cooled, he x-rayed the glass and found that there were tiny copper chloride crystals that formed the glass. When he shone the light on the glass, the biggest crystals behaved the way copper chloride would do. But the smaller the crystal size, the bluer the light the crystals emitted. He was well aware of the literature in the West, well acquainted with the laws of quantum physics. He absolutely understood what he had done and realized that he had observed a size-dependent quantum effect. He published, and happens to people, he published his findings in a Soviet scientific journal in 1981. Well, who read it? Because another guy found the same thing 2 years later. Who's first? Okay. The Nobel Committee does do its homework, and hence he's included in the group. They recognize that Louis Brou did not know about that work, and he wasn't trying to jump the gun or fib. Notice another one, Bell Labs, one of the most innovative labs in the United States in that time period. It followed the pathway here in the science. He was working on something different. He was developing these cadmium particles to capture light and harness their energy to drive chemical reactions. He wasn't interested in dots. That's what he wanted to do. He made them as small as he could. Why would you make it small? Because more surface area. If there are many more, if the grains of salt are very much smaller, the salt's much more reactive, right? The sodium chloride crystals are a lot more reactive because more of it is exposed. All right? Again, he's not thinking about quantum effects here. But here's the kind of thing, success or failure comes with this. He noticed that the optical properties of the particles, so he left this thing out on the tabletop in the lab. And he came back to find they were behaving differently. And he thought, gee, what's going on? Well, the crystals are growing. And in growing, we're emitting red light, not blue light. So, very, very clever idea. His hunch was vindicated when he prepared fresh, smaller particles with the larger ones, and so on. So he published these findings 2 years later. Okay? So, independently, truly independently. Now, periodic table. I'm not going to get into the periodic table, except to say a substance's optical properties and enzymatic properties and their ability to conduct electricity is related to its electrons. The electrons are the kind of the matriarchal components of atoms. I'm not sure what the atom actually does, except make atom bombs. And that kind of thing. But electrons, and it's not any electrons. It depends on the number of shells, or energy levels, with which they occupy, the number of shells, but especially on the outermost shell, and whether that outermost shell is full, has a full complement of electrons, or fewer. If it has fewer, it's not looking for, we'll say that, looking for other atoms to share their electrons with them so that they can have a more complete outer shell. What's that called? Marriage making or bond making between atoms to form molecules.
right? That look fundamentally different. I mean, just look at sodium chloride. Chlorine. Chlorine looks very, very different than the crystal, sodium crystal. But combined, right, they look quite different and the properties are very different. How does that happen? Because of sharing electrons. Water is another one. Right, so you're really combining oxygen with two hydrogens. The hydrogen is kind of loading, if you like, its single electron out, so oxygen can more completely fill its outer shell. So therefore, the molecule is polar, meaning there are more negative regions and one positive region in that molecule, which makes it the ideal kind of cleaning fluid. Water has amazing properties, but that's one of them. And it's related to its atomic structure. So, so quantum mechanics actually is important. Buwandi, you know, in the early days when they were playing with this stuff, the whole thing, it was fairly rough. But to turn this into a commercial venture, they needed a way of creating these dots so that they were precise. They were absolutely uniform across it. How do you do that? Well, that's chemical engineering. My dad was a chemical engineer. That's what engineers do. They figure out how to do things like that. And there's the kind of the experiment. He injected substances that can form cadmium selenide into a hot solvent. So there's the hot solvent here. There's the needle, a syringe right here, stabilizing gas, a thermometer there. And what would happen is the crystals would form. If you injected enough of this, the solution became saturated, and the crystals started to form around the needle. And if you stopped it right there, or by controlling the time that went by and the temperature, you could get very precise sizes in these particles, in these nanoparticles. So very precise control of the size, and that was the critical thing. Now look at this. This would be unthinkable 5 years ago. You were looking at 3 cells. There's one cell, there's another cell, there's another cell. There's the nucleus. It's the nucleus. This is using these nanoparticles. And the microtubules are the QEW. They are the highway system of the cell. They transport stuff from one place to another. That's what they do. They send messages, various molecules, but mostly kind of messages or structural components back and forth. Look at them all. It's worse than anything around the golden horseshoe. And guess what? All of these little red things are in there. The males in this room, including me, don't have in sperm. They're mitochondria. They are the energy source for things. So mitochondrial disorders are traceable to females because they are the ones carrying mitochondria if they're abnormal. But they also provide the energy for the cell, which they need with the embryo, growing embryo, right? Makes sense to give them the mitochondria. But look at the incredible detail of that. Isn't it, I started with the 4th or 5th slide and I said biology's complicated. It is, it's stunningly complicated. We're talking about one cell here, or 3 cells. And you're only looking at 3 components of it. This really caught me. This is very complex, but let me just say, if you use different light sources, therefore different wavelengths, and project them, say, onto the hand, you can see the arterial supply, the venous return from the hand non-invasively. Isn't that beautiful? By combining X-ray
with a visible light, infrared source. And so there's the picture over there on the right-hand side. Gee, that's another thing that neurosurgeons and other surgeons want to know. What's the vascular supply of the tumor? What can what should I be very aware of and stay away from? What should I preserve? What's feeding this tumor? And so it's a wonderful technology. It really is. And this is just on the edge of things. When I thought about this, as time goes by, remember the series? Yeah. There's a wonderful one, which I thought was analogous to what we've been talking about this afternoon. Remember the one where they're about to get married, and they're going to have the reception in her home, or their home, Lionel, together. And I've forgotten how many people, but they're trying to jam them into a small home. And so Lionel had it all figured out, calculated out how many people he could get into the room. And so there was quite a little discussion between the two of them, and he had it all figured out. And Judy Dench said, well, there were kind of 3 or 4 people. He said, well, you could just stand here and hold it was a wonderful thing. And I thought today, when I was going over this stuff, well, it's just like these electrons in cells getting crowded together, the smaller they are. So I think it's a kind of a sweet analogy, squeezing bodies together. Now, the present and future, well, it certainly makes money, $4 billion. It's up by $2 billion when I checked yesterday. Quantum dots, anyway, map blood vessels, we actually saw that. You can track drugs within the body. That's actually a very helpful thing to do. It certainly makes more efficient solar cells. You can collect more energy. And it can serve as gates and switches in quantum computers. Note quantum computer, not the one you've got at home. Quantum computers, that's the next edge of things. So you don't need to hear the quantum. Yeah. Well, here's the last one. I like this one. This is the fellow in Russia, the chief scientist at the Moscow Institute of Radio Engineering. He published a paper, who would pay any attention to method of edge waves and the physical theory of diffraction? Really? It's one of thousands of papers that the CIA translated. Fortunately, somebody at the Skunk Works read the translated version and realized it was the answer to stealth technology. So the Russians, who were slow in adopting that kind of stuff, kind of 20 or 30 years behind the Americans, were actually ahead of it. And it reminded me too that Russia, USSR, and in present form, have a very strong tradition of excellent engineers. And in science and mathematics and physics, we kind of forget that. And this is only one example of that. So, and just finish out one last slide. These are nanoparticles. One of the issues with the James Webb Telescope is when did the first stars develop in the universe? Well, initially it was around 1 billion years or 800 million years after the Big Bang. And then the Hubble telescope, with a bit of a stretch and help, kind of pushed that back to say 400 million years. 400 million is a lot of years, but 400 million years. That's a big shift. Well, then what they found just recently is that there are nanoparticles made out of carbon in space that can be picked up with the Max Planck, or not the Max Planck, what was it? They had it 2 seconds ago. The telescope, James Webb Telescope, to pick up these graphite
particles. Now, the importance of carbon, carbon is made in stars. And it requires certain gravitational pressure and temperatures to make it. And the earliest stars were very simple affairs, just made of hydrogen and some helium. That was it. No carbon, no other elements. Well, if you're finding complex stuff like carbon here, and you're finding it 400 million years after the Big Bang, it implies that stars were making that, because that's the only source for such carbon molecules, much earlier. So the standard model, this is another lesson in science. Science creates standard models for quantum mechanics, for the early evolution of the universe, because they serve a purpose. They provide a framework for thinking about it and for creating experiments and to make observations, to be tested. That's what models are for. Not that you're going to believe it. Again, remember, it's the evidence that counts. Okay, these are working models. Most of them are computer models. That book I sent around is written by just such a guy. That's what he does. That's his job every day. So, but the standard model for the early universe is in trouble now, because it seems that a lot happened a lot earlier. And how did it happen? When did dark matter come about? How did the stuff start to clump a lot earlier? And if it did, why? To form stars and galaxies. And if that's wrong, what else is wrong? So it's a window into, again, how science works. But to put it in perspective, you realize that in 1900, no one knew any of this. Not any of this. Not quantum mechanics, not any of this stuff. They didn't even know much beyond their small corner of the Milky Way. And I don't think there's any other time in human history where so much has happened in such a short time. And it's probably related to, okay, that's enough. Okay. I have a great fetish for footprints, not feet, footprints, especially old footprints. And David Elkins and Valmai Elkins might recognize the area because New Mexico's white sands. Yeah, right. These are footprints that have revolutionized how we think, or when people migrated to the Americas. Because up to then, the evidence was something around 15 to 18,000 years ago, after the Ice Age was beginning to recede. Ocean levels were going up. You could actually think about land bridges. But it turns out, at least at this white sands place, that they migrated much earlier. In fact, smack dab in the middle of the last glacial period. Can you imagine crossing over from Asia to the Americas under forbidding cold, ice and snow, presumably lots of fish, and probably woolly mammoths, that kind of thing around, and seas that were much lower, maybe several hundred feet lower, because water was all taken up with the ice. Right? So this kind of stuff. But the reason why I really am attracted to feet is somebody made those prints. And it is intriguing to ask, well, who were they? And it isn't just one set of prints. So who was with them? And what were they talking about? Were they talking about quantum mechanics? Something like that. So it's they're very intriguing. And of course, there's later prints. David and Valmai would know about 8,000 years ago that are the most intriguing for me. They're almost poetic, because they appear to be a female, a young female, who from time to time is carrying a child, because you can tell from the weight distribution of the feet that she's carrying a child on her hip. And then from time to time, she, I don't know whether the kid was wiggling or whatever it was, or just she was tired, let him down. Two prints become 4. Little prints and bigger prints. If you follow the track along, it's about a mile track. A woolly mammoth crosses the path, pays no attention to it. And then they run across a giant sloth. Well, a giant sloth is taller than anyone in this room, and a good deal more powerful. And it did apparently stop based on the prints, and in our imagination looked at them. But the prints from the woman didn't speed up or slow down. And then the sloth went on its way, and that's all you know. Couldn't you love to know where's the family? Were there other children? Where was she going? She was unhurried, not in a rush. And that's why footprints tell us more than looking at skulls. We don't actually know what's going on in that brain from looking at a skull, but we have a good guess at it by the behavior left by footprints. So that's the thing. So next week we're on the more prosaic stuff, the vaccine story, except that the human part of that is really, really interesting. So we will see you next week. Yes?
So, very recently I was on a new jet aircraft and sitting there, and in order to make it darker in our seat, we were in a window seat, you press a button
Yeah.
and the glass becomes opaque at your touch.
Yes.
And then if you want to make it lighter into the cabin and see outside, you press the button and the glass clears
I wonder
up.
if the glass is polarized.
Yeah, but I wonder, is that working on quantum?
No.
No, it's working on something else.
Yeah, it's working on something else. Yeah, that's not a problem. But do they have this all worked out to get back to this? Do they actually know what these electrons are doing? Well, last week was developing the technology to actually study the electrons,
Right.
so you could see what they were up to, which might tell us what they're actually doing in these studies. So the two studies come together, don't they? They start to merge, even though the two groups aren't talking to one another. They would be aware of one another, reading one another's stuff, but actually not much. So, and it does put a stamp on the importance of really good centers, this kind of stuff, and also the risks of that kind of thing, right? Because they're not evenly available for everyone. There isn't equal access. That depends on money, influence, family connection, especially places like Harvard, because, well, they got into trouble just recently in the news, didn't they? Because they've always had this policy that if your father or mother went here, or the grandparents went here, you don't automatically get in, but you have a much easier way, pathway into it. Now, is that a bad thing? Probably not. What's bad about it is not providing the opportunity for the others. That's what's bad about it. So, unless you've got any other thoughts? Yeah.
You mentioned something about in gene editing.
Yes.
Next year there was going to be a dramatic change in vaccines, was it?
Yes. Yeah, I think it's probably going to happen with the COVID vaccine and with the flu vaccine. I think people are kind of tired of the fact that and COVID really brought this out, but the flu has been with us with the same kind of behavior for a long time, meaning the strains change quickly, they adapt. But even if it's the same strain, the effectiveness starts to decline around the Israeli study showed around 4 to 6 months, and doesn't offer much protection much beyond 9 months. Well, that's why we had multiple shots. But you notice what happened with the province here. I mean, this is very costly running these programs, and everyone was out and doing their thing, and in a way, kind of went to sleep. But it's really important for us, people that look like us, to have that updated vaccine. Oh, well, get back to what would be the fix. Is a so-called universal vaccine. What's a universal vaccine? If you look at the COVID virus or the flu virus, all the parts of that virus, by the way, it includes a lot of proteins, a lot of very complex proteins. The mRNA, or DNA in some cases, mutates. But some areas are much more likely to mutate than others. Others are what we consider conserved, meaning they mutate hardly at all. So why not make a vaccine out of the most conserved proteins in the virus? So you don't have to worry about seasonal changes. You still have antibodies and a cellular response to the virus. Now that proposal was made by Anthony Fauci early in the pandemic, or at least it was proposed to him and his working committee. And his group thought it was very promising, but they didn't fund it, which is always a message. But on the other hand, at that time, everyone was in a rush to get on with the mRNA vaccines were there. They're very effective, very effective. I'm not knocking them, they're very effective. It's just not effective for long. But so that proposal didn't get a lot of traction. Then it was brought up by Fauci himself, and he wrote an editorial in the New England Journal of Medicine about 3 or 4 months ago to say this is where to go with for flu and for COVID, and frankly any other virus. And it certainly makes sense to me. You want to present, you want to put the best antigenic footprint out there, the one least likely to change, and that is these most conserved portions of the virus and the protein. Yeah, Sheila.
Yes, just on the stealth bomber, which you mentioned,
Yeah.
because all the information came from Russia, as you know.
Yeah.
Russian scientists turned, whatever you call them, traitor to Russia. But
Well,
I
he
don't.
wasn't a traitor. He actually treated well.
Well, he worked,
Yes, he
there.
did. He did.
But the lovely thing is that he would take the plans from his office and lab in his coat pocket, out of his office into the street, get them photographed in his apartment, send them to the CIA, then come back, having had a lovely lunch at home with the plans. And he did that for a number of years until the Russians decided they needed more security, couldn't understand where he was coming from. I mean, incredible that he could walk in and out of that building with this highly secretive
Well, what do you
information
think's been happening?
in his coat
What
pocket.
do you think's been happening for decades in the U.S.?
Well, tell me, I don't
It's
know.
got to be the leakiest country in the world with its secrets. And this kind of stuff's been going on. And the other thing to remember, understanding stuff is universal. The science is universal. It's very hard for one country to corral it. Especially, say, for example, like the United States. If you attract a lot of graduate students from China, as has happened in the last 30 years, they're not all there as spies. Maybe 1 in 1,000 or 10,000 are, I don't know, but the rest of them are there. They want to learn the expertise.
In this particular case, of course, it saved the Americans an enormous amount of money in research, because all the research had been done by the Russians and now the Americans had it.
And the Brits, for example, profited a lot by us and Australians and South Africans and everyone in the British Empire going to the UK. they were freebies. They didn't have to pay for them. They were all nice grants. And they were intellectual freebies. They got the brightest people that the Commonwealth and Empire had. And, and they shared the stuff with it. I mean, the period when, the first time I was at Oxford, it was incredible. I mean, you could, Sherrington's old lab there was about 90% populated by Americans and or North Americans and British Empire and Commonwealth people and some Europeans. It gets to this whole business. I mean, I mentioned this to several of you before, but if you look at the top 10, top 20, top 50 universities in the world in the sciences, most productive. What do I mean by productive? Citation index. Number of times your paper has been read, paid attention to, led to something. China's gone from 0 to 1 to 2 to 3 in the top 10. And if you want a marker for that, Oxford and Cambridge are in the second 10. And if you want a marker for the U.S., quite uniformly distributed through the 50, but not growing. Yeah, and and it isn't just that. I mean, you'll be the same with Singapore and all of those Southeast Asian countries, highly educated people. They're all hungry. They all want to join the game. India now is really very productive, and why wouldn't they be? And they've won their. By the way, do you know that Canada's won 26 Nobel Prizes? I didn't know that until I actually looked it up. 26, and not just Bandy. 26. And if you compare it to the U.S., what do you think the U.S. is? Yes?
260?
400.
Wow.
400, yeah. Those are in science. I'm talking about science. I'm not talking about economics, or the Peace Prize, and or literature prize. That's a whole other matter that I'm sure that we'll hear more about later. But anything else? Where you're completely swamped with quantum dots. By the way, did you notice in that one slide, going back, did you notice Q dot? What does Q stand for? Quantum dot. So that's the crystal that was used to generate green, red, and what was the other color? No, I got to catch it up. Yeah, just the green and red. So anyway, so they use quantum dots too. That's why all these mitochondria and these microtubules are all standing out like crazy. Okay. All right. So on to next week. Oh, wait a minute. Before you go, after the last paragraph of the slide.
Oh, yes.
You have to hear that. So I finished off here. I said, my father would have known nothing of this, that being all the stuff we talked about, or the exciting work which led to so many Nobel Prizes in closely related fields. But he was a well-read, curious man who kept a microscope on his desk at home and used it to explore his environment. He was a naturalist. And died in the 1970s, so I said, I think he would be proud that eventually my son took an interest in chemistry and physics beyond what I needed to know for practical medicine. So there we go.